Hello everyone, Assalamu alaikum. Welcome back for another video in the series. In this video, let's dive into the topic of logistic regression by viewing it as a single layer neural network. This is why I emphasize the identity function in Adeline so much, because if you look at this figure here, this is a single layer neural network where we have the inputs x, the weights w, and then we compute the net input here and the activation here, and then an output here where we, for example, could apply a threshold function, but for training we can ignore the threshold function. We usually use the output from activation. So in Adeline, this activation function was an identity function, and in Adeline then we use the mean squared error as a loss function. We computed it between the activation and the true class label. So here A, this is the activation here, and then we had some true class labels Y and computed the mean squared error. Now the only difference between Adeline and logistic regression is that we have a different activation function. So one difference is that we now use this logistic sigmoid function instead of identity function. So in Adeline, again, we had just the identity function Z. So input Z and output Z. Now we have this nonlinear function. I will show you in the next slides how it looks like. And another difference between logistic regression and Adeline is that now we have a different loss function. So here is how the logistic sigmoid function looks like. There are two forms that you can represent it in. Usually this one is the more common form in deep learning contexts, and we will be using this activation function also in the context of multi-layer perceptrons later. So how you get from here to here, from the left hand side to the right hand side, is just by dividing by e to the power of z. Alright, so here's how it looks like. So we have an activation here plotted on the y-axis and the net input, which is passed to the activation function on the x-axis. So this is really the input to activation function here, and you can see that it's centered around 0. And if the input is 0, then the output will be 0.5, and it saturates here at 1. And here on the other hand, it approaches 0, so it's a function between 0 and 1. But you can see you have to have very negative or very positive values. So this is how this function looks like. Now I will explain to you how the logistic regression loss function works, like in the next video. Here, I just want to summarize a few things, and it may be that you have to think a lot about this because it can look a little bit complicated at first glance, but essentially it's not that complicated. So let me just use this notation here to summarize the logistic regression model, where H, you can think of it as a hypothesis in traditional machine learning, or you can, in more simpler terms, think of it as the model. And this is our logistic regression model, which receives as input the net input, and then you have this logistic sigmoid activation function that I showed you in the previous slide, which returns a value between 0 and 1. And you can actually think of this whole model here as the model that computes the posterior probability, the probability of class label y, given a feature vector x. So y is the class label and x is the feature vector. So you can think of it as this. So let's look at a concrete example. Let's consider the iris dataset where we have class label 1 and let's say setosa for simplified case. Think of it as a binary classification problem. We have 1 as setosa and 0 as versicolor. These two classes. Now if I want to compute the probability that a given feature vector belongs to setosa to class 1, I can write it as this. Py equals, let's say, 1 because it's shorter, given x, and this is computed as this one, and the probability of y equals 0 is computed as x, which we can write as 1 minus h of x. So these are the feature vectors here on these x's. Now imagine the probability for setosa is 0.8, then equivalently the probability for versicolor would be 0.2, right? So if this is indeed true, if the flower is indeed setosa, then this would be actually a pretty good probability. So let's say we assume we have a true label. Let's assume that a true label is actually 1, then it would be actually pretty good to get an accuracy of 80%. The higher the better. So we want to actually have a high probability. But if the true label is 0, then a high probability would actually be bad. Like if the true label is 0, what we want is actually a high probability for py equals 0. Then if the true label is indeed 0, then we want to have 80% maybe for this case. So that is what I'm summarizing here at the bottom of this slide. So if we have a binary classification problem with possible class labels 0 and 1, what we want is these probabilities to be closer to 1 for the respective class. So if the class label, the true class label is 0, then we want the probability for y equals 0 to be close to 1. If the true label is 1, then we want the probability for this scenario to be close to 1. So in this case, it's depending which probability we want to be maximized depending on the true label here. So we will look at that, how we can do that with a loss function in the next video. But this is like the basic setup. So we want a high probability given the other certain class. So vice versa can also be done for Setosa as well. I hope you understand the basic idea, and we'll explore more in the next video. If you have any questions, feel free to drop them in the comment box below. See you in the next video.